So a quick review of everything, because this was a lot of material. We started off by reviewing last lesson's previous steady state response findings. And we said that if we've got this complex exponential input, we get a complex exponential output, just modified by a complex number, which is the transfer function evaluated at that complex frequency. And we said this is great from a theoretical standpoint of view, but we don't really have e to the j3n's bopping around in real life. We have real valued signals. So how can we make this useful in the real world? Well, if we've got a cosine input, a pure cosine input, that's sinusoidal steady state, it means a 5 cosine of 3n. It means that 5 cosine of 3n in gives us a 5 cosine of 3n out, just modified by a difference in amplitude and a difference in phase. And that amplitude and phase are the amplitude and phase of the transfer function evaluated at an omega, which is the input frequency. We said that there's a power series input too, which we see all the time. And that's actually equal to the same thing as this complex exponential, but just now this frequency looks really weird. It looks like a omega naught, which is 1 over j times ln of whatever our power sequence is. Kind of weird, but it works the same way. It means that if this is our steady state input, our output is a steady state input, just multiplied by our transfer function, evaluated at that really weird looking omega naught. We said that an input that switches on at n equals 0, and that 0 before n equals 0 is a causal input. And unfortunately, everything that we studied last class with steady state responses only work for non-causal inputs, for inputs that have been on forever. So how do we make those results work for causal inputs like we see in the real world? Well, we can always just ignore what we did last class and just do Z transforms. So if we do Z transforms, we get the exact response. Or we can say that even for a causal input, our output will be that part which is steady state plus a transient decaying part that's caused by the fact that the input suddenly switched on at time equals 0. And the transient part will decay. So we could get a pretty good approximation for our output by just simply saying it's a steady state response. In the particular case, and that works always, but in the particular case that our system is order 0, meaning that it has no negative feedback, that means that the impulse response is going to be finite length, and that means that the transient response will exactly decay away by the mth sample. And that means that our output is exactly equal to the steady state output for any n greater than or equal to m, where m is the greatest power of z in the numerator of our transfer function. We worked out an example where we found out the output of this power series, both exactly and using this approximate steady state response. And we said that since this has a m of 1, 0 order still, right? Because it's a finite impulse response, but it has an m of 1. Therefore, its output steady state response is going to be exactly equal to its exact response for any n greater than or equal to m, which in this case is 1. And what we did on the right can be done by microcontrollers, can be programmed a lot easier than doing divisions and by doing inverse Z transforms on the left. So as long as you've got an FIR system, you can exactly characterize its output for n greater than m by just finding its steady state response. Even if it's infinite impulse response, we still get a pretty good approximation of it because, as we saw in the previous slide, the output is equal to the steady state plus the transient, and the transient decays away pretty fast. The last part that we talked about had to do with delays. And we start off by talking about the system phase response, and that's how much phase it adds to a constant frequency input signal. And we said if it adds more and more phase as the frequency goes higher and higher, if it delays it by more and more, that means in the time domain, it's actually just shifting things over by a constant amount. And we showed that both intuitively and by math. And so we said if we see the system phase response as a straight line, then our system is a pure delay, and it delays it by minus slope of the line. So whenever you hear the words linear phase, what I want you to think about is a constant delay, a system that delays things by a constant amount and doesn't change the shape of your signal. The last part of our lesson took a look at system delays. And there's several different alternative definitions for system delays, and we looked at one of them called group delays. And the group delay, the intuition is that if you have a sudden spiky input, your output is going to be probably spiky too, but it will be delayed. And how much is it delayed? It's delayed by the group delay amount, by the tau sub g. And how do we define this tau sub g for an arbitrary system? If we're lucky enough to have a linear phase system, a system that has linear phase, then we just take then by definition of linear phase, the phase response is a straight line, linear. We take a look at the negative of the slope, and that's the delay. Well, that's pretty easy. And we can find that in particular in FIR systems. There are FIR systems that can have exactly linear phase, and that means it will have a constant group delay regardless of the frequency. And that means it delays all the frequencies by the exact same amount in the time domain. Linearly increasing phase in the frequency domain corresponds to constant delay in the time domain. And that means it doesn't change the signal shape. And that's usually a desirable characteristic. But if we've got an IIR system, we're guaranteed to have a non-linear phase response. And then that group delay is going to change with frequency. And one reasonable definition for that group delay is to take the negative of the slope. So if the slope is constant, then we just end up with what we expect. If the slope is changing, then the group delay is equal to the negative of the amount of slope, the derivative of the phase function with respect to omega. And that tells us how much it delays things at different frequencies. And if it's nonlinear phase, then we have a non-constant tau sub g, a non-constant group delay. The amount that it delays a signal in the time domain is going to be a function of how high the frequency is. And that means that it's going to delay different frequencies by different amounts. And that means it's going to change the shape of our signal, which is generally a non-desirable characteristic. And that's everything in this lesson.